My name is Aaron Anderson, and I'm going to be teaching about aliasing in the context of a digital signal processing course. As background to why we need to learn about aliasing, this is a problem that can occur when you're sampling a signal. So sampling is the process by which we convert an analog signal in continuous time to a digital signal in discrete time. And so this is a useful process, and to explain it, I'm going to draw. First, if we have a continuous time signal, in this case x of t equals cosine of t, then we have values at every point in time, and this continues. And when we sample it, then we just grab specific values of that, so I'll mark them with an x. In this case, we're going to sample with a period of pi over 2. That means at x equals 0 and every integer multiple of pi over 2, we grab a sample. And we're going to call that signal xd of n. The square brackets in the n indicate this is a discrete time signal. And this is then going to be cosine of t over, we're going to use capital T naught to represent our sampling time. And then to draw this in discrete time, I'm going to sample here, 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 and here. This equals to 1, and this equal to minus 1. And this is n and xd of n. Okay, and in this signal, you can still pretty clearly imagine the easiest sign to fit is this shape cosine, which is exactly what we intend to be representing. Now, if we change our sampling period, instead I'm going to redraw t and x of t. I'm going to draw it a little bit longer, actually. So this is going to be 2 pi, pi, 3 pi, all the way to 4 pi here. Now if we imagine sampling, I'll use a circle to indicate it's a little bit different. Instead of sampling, as we did here, pi over 2, now we're going to use a sampling period of 9 pi over 10. And so that will be at 0, at 9 pi over 10, at 18 pi over 20, which is a little bit below 2 pi. And continuing on, grabbing these samples at, progressively a little bit farther behind multiples of pi. Now when I draw this in discrete time, xd of n, we've got our first sample is up here at 1. Our next sample is here, and its value is, say, a little bit less than -1. So if we imagine -1 is there, it's a little bit less than -1. Our next sample is here, you can see, is a little bit less than +1. Our next sample here is even less, even closer to 0 than the previous negative, etc. So we're going to get a pattern that looks something like this. Now, just looking at this discrete time signal, if you're going to reconstruct it, you could maybe look like a decreasing zigzag, but if we restrict ourselves to pure sines or cosines, which for this example we're going to, then the easiest one to fit is going to be the correct one. You can imagine this fitting in there. I've drawn it imperfectly, but the idea is there. And then, so these two are two examples of continuous time signals with a sampling period, which then yield discrete time signals, which we can sort of visually, you can see where the original signal fits in. Now I'm going to draw another one, this time with the sampling period 3 pi over 4. Redraw my cosine. Let's draw squares. So if I sample with 3 pi over 4, this is pi, 2 pi. My first sample is here, and then another 3 pi over 4 is going to be at 3 pi, and the following, continue the signal on, the following will be here, and then up here, back at value of 1. So if I draw this now in discrete time, you can see our first sample is 1, our next sample is 0, then -1, back to 0, +1. You can see the pattern. And so the easy cosine to draw here would be this one. The only problem is, if we look at our original signal, we have a minimum before hitting this one. So our original signal is actually this one. And so if we continue drawing this, we would see that the signal that we can easily draw here, the lowest frequency that fits, would have a frequency of 1/3, or a period of 3 times the size of the original. You can also sort of see what we would pick up if we draw it here. So that is, in short, aliasing, where we pick up a signal that's not actually there because we used too low of sampling frequency. But when we used a higher sampling frequency, we didn't see this problem. So now I'm going to explain mathematically what's happening by looking in the frequency domain using Fourier transform. So we're going to start out on this side. And for this one, I'm going to assume that you already know that the Fourier transform of cosine of omega t, or 2 pi f naught t, the continuous time Fourier transform of that is 1/2 delta of f minus f naught plus delta of f plus f naught. And so the continuous time Fourier transform of this is, see here, 2 deltas at 1/2 and, or at height of 1/2, or scale to size of 1/2, positioned at plus and minus f naught. In this case, our f naught is 1. That's the continuous time Fourier transform. And space. Next, we're going to go to the discrete time world. So I'm going to now calculate the discrete time. The discrete time Fourier transform. So if xd of n equals cosine of n over t naught, this is equal to and for that is equal to E1, equal to 1/2 times quantity e to the j f naught t naught plus e to the minus j f naught t naught. This is if we've got f naught in there. And the Fourier transform of complex exponential is a delta. And so when we have this in discrete time, though, we've got a repetition. I'm glossing over a little bit the details here, assuming you've already seen discrete time Fourier transform of sinusoid. And so this is going to be 2 pi, and then I take this coefficient out, so 2 pi over 2, repetition every 2 pi of delta of omega minus f naught t naught plus delta of omega minus plus f naught t naught. And so this works out, the 2's cancel, and this comes out to, in our first case here, pi times rep every 2 pi of delta of omega minus pi over 2 plus delta of omega plus pi over 2. And making myself a little more space here, if we draw that omega x of omega, its delta is scaled by pi at pi over 2 and minus pi over 2, and then we repeat this every 2 pi. And so when we repeat that every 2 pi, this one repeats here at 3 pi over 2, and this one repeats up here at 5 pi over 2. And these continue on rep every 2 pi. So we can see here clearly between negative pi and pi our original Fourier transform, and then repetitions above and below. And they're reasonably, we can say, well behaved. Next, if we imagine instead of pi over 2 here, we have 9 pi over 10, as in our second example. I can draw that as well. If we have pi here, we're going to have delta scaled by pi at 9 pi over 10 and minus 9 pi over 10. And then the next repetition will be here at 11 pi over 10 and 19 pi over 10. And so you can see here there's still a little bit of a gap. The arrows don't overlap. So now going to draw the frequency frequency domain plot of this one. So if we have pi minus pi, our deltas are going to be, instead of pi over 2, they're going to be 3 pi over 2. So all the way up here. And divided by pi. And this is going to be negative 3 pi over 2. Now, when we repeat this every 2 pi, negative 3 pi over 2 plus 2 pi comes out to pi over 2. And 3 pi over 2 minus 2 pi, or the previous one down here, if you want to think of that, comes out to minus pi over 2. So, and this is of course repeated every 2 pi, but we can see now with the repetition, we have deltas at pi over 2 and negative pi over 2, which are closer to the center than the original signal. And so this is going to come out looking a lot like something else. And this is the problem when our deltas cross over each other, essentially. And so in order to get understanding what this is going to do in the time domain, if we inverse Fourier transform this, we can imagine reconstructing this, and these deltas correspond to a frequency of pi over 2 is the omega, and then we want omega times 1 over t naught, so that's going to be 1 over 3 pi over 2, and I wrote this wrong up here. This should be 3 pi over 2, like I drew, but wrote it wrong. So this is 1 over 3 pi over 2, and that's equal to 1 over 3. So that's the first frequencies we see in the Fourier in the frequency domain. Fourier transform are these at negative pi over 2 and pi over 2, which correspond to a frequency of 1/3. And that's exactly what we see here. That this line that we use to connect our samples is at 1/3 of the original frequency, a frequency of 1/3. And so that is aliasing. That's where we see what appears to be a lower frequency and a higher frequency signal that's sampled at too slow a sampling rate. Now, to generalize this, we can do this, of course, with any signal. And as we know, the Fourier transform basically tells us that pretty much any reasonable or well-behaved signal can be represented as a linear combination of sines and cosines. And so if we imagine ourselves, say, some weird time domain signal whose Fourier transform is, say, a triangle with maximum of a and negative a. If we sample this, then we're going to have a repetition every 2 pi. And let's say we sample this at a very high sampling rate. We're going to get this repetition every 2 pi, and there'll be plenty of space in between these two. This gap will be really big, and so to reconstruct, we can just low pass and reconstruct from that, so there's no overlap between the two. But if we imagine instead, as we increase the sampling period or decrease the sampling frequency, these stretch out, they get wider. And so if we let them get too wide, we can then have them overlap. in the adjacent repetitions. And this overlap is a big problem, because then if you imagine adding these together, we get something like this, once you add it up. And when you get a Fourier or a frequency domain signal that looks like this, you can't know if maybe this one originally came off and then dropped off sharply, or if it's too overlapping, or what. You just can't know what your original signal looked like, and you get aliasing. And so that's essentially what aliasing is and how we get it, explained both visually and with some math in the Fourier domain, the Fourier transform, frequency domain. And there are plenty of examples of aliasing that we can see in real life. This isn't just some abstract mathematical concept, but it's something that you can experience frequently. For example, I didn't just wear this shirt and tie because it seemed like a nice idea. This shirt has narrow vertical lines. That's essentially a square wave, I guess, across this dimension in space. And so that is then sampled by the sensor on the camera, and that is processed and dealt with, and then sampled by displaying it as little pixels on your screen. And so if those sampling periods are too small, you're going to get weird artifacts that, that don't look like these narrow vertical stripes that the shirt actually has, but you can get all sorts of interesting patterns. And hopefully, you don't say this very often, but hopefully the way it's displaying on your screen looks bad. It looks really weird because it's got the wiggly things in your shirt. If it's not, what you can do is in YouTube, in the lower right corner, there's the gear. You can click on that and change the quality. If you adjust the quality of the video, you can change essentially the spatial sampling frequency, and as you adjust that, you should be able to hopefully find some quality that will show that to you. If not, I'll also put a link in the description below of a video that really clearly shows it. So yeah, my shirt, maybe my tie, we'll see, should show some spatial aliasing, essentially. There are plenty of other examples that you can see. For example, often called the wagon wheel effect, is where wheels are spinning and there's a video camera taking, and it looks like the wheels or wagon wheels are traveling backwards when obviously they're traveling forward. So you can pay attention to the world around you and see plenty of examples of aliasing in real life. This morning I noticed the screen on the window. It caused aliasing in a couple things I could see outside. So it's all around us. And that is aliasing. Thank you.